Hello everyone. Today we will study in detail about thermochemistry. So let's start. Disclaimer slide which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@rtk.ac.in and we shall remove the images. Let's start with the index slide. These are the major topics which we are going to study today. First, thermochemical standard state, heat or enthalpy of a reaction, factors influencing enthalpy of a reaction, types of standard enthalpy of reaction, Hess law of constant heat summation, bond energy or enthalpy, factor affecting bond enthalpy, calorimetry, constant volume calorimetry or BombCalorimeter. So let's start with our first topic, that is thermochemical standard state. Thermochemistry is a branch of chemistry which deals with energy exchange between a chemical system and its surrounding. Heat is generally evolved or absorbed whenever a chemical reaction takes place or change in the states of matter occurs. Change in the state of matter like vaporization from liquid to gas, fusion from solid to gas, phase transitions, etc. Right? So in the thermochemistry, we will study about the change of heat or energy and the change of states of matter. Okay. So thermochemistry focuses on these energy changes, particularly on the system's energy exchange with its surrounding. So basically, we are talking about the energy changes here. So energy change in terms of like system's energy exchange with the surrounding energy. Okay, we will see that in detail. The heat change accompanying chemical reactions or physical changes are measured experimentally with the help of calorimeter. So calorimeter is a device through which we can change that what amount of heat change has been done during a chemical reaction or any physical change. Okay. So chemical reactions are invariably associated with transfer of energy, and most frequently energy transfer in chemical reactions take place in form of heat. So if you observe generally, it happens that chemical reactions involve the transfer of energy, and the transfer of energy happens in the form of heat. Reaction may be exothermic or endothermic, and on the basis of transfer of energy in the form of heat, we can divide our reactions in two categories, that is exothermic or endothermic reactions. So what happen in both of these will be exothermic reactions transfer heat to the surrounding. So in the exothermic reactions, the heat will be transferred to the surroundings. So while while any reaction is happening which is exothermic in nature, the heat will be transferred to the surrounding during the reaction. For example, here is a reaction given here. 4 aluminium atoms is combining with 3 molecules of oxygen, giving aluminium oxide 2 molecules, right? And heat is evolving in this reaction, that is this exothermic reaction, and heat is transferring to the surrounding, which is measuring as minus 1676 kilojoule. Note that the delta H, that is change in energy or change in heat, is in negative sign here. Okay, so we can say that in exothermic reactions, the measure of change of heat which is transferred to the surrounding should be in negative. Second type is endothermic reactions. In this type of reactions, they transfer energy or they transfer heat from the surroundings. So they take the heat while performing any chemical reaction. Okay, so like this example is mentioned here, that N2 will react with the O2 molecule, giving the nitric oxide, and the heat is absorbing in this process. So del H is plus of 90.4 kilojoule, right? So del H will be in positive sign here, note, right? So in the exothermic, we can say that del H will be in negative sign, and in the endothermic, the del H will be in positive side. A thermochemical standard state of a substance is its most stable state under standard pressure, that is 1 atmosphere pressure, and standard temperature, that is 298 Kelvin. Under these conditions, any parameter is designated by the superscript theta or 0 or not, we can say. Okay, so we are defining here a thermochemical standard state of a substance. So the standard state of a substance is the most stable state under the standard pressure and standard temperature, that is 1 atmosphere and 298 Kelvin respectively. And under these conditions, any parameter, if we want to state it as standard state, we put a superscript on that, which is either theta or naught or 0, you can say. So for a gas, the standard state is considered at a pressure of 1 atmosphere. In a mixture of gases, its partial pressure must be 1 atmosphere, right? So if we take the state of a matter like gas, the standard state is considered at 1 atmospheric pressure. And if we are taking the mixture of gases, then their partial pressures, that is, every gas has its own pressure. So the partial pressure of every gas must be 1 atmosphere. Okay, the sum of partial pressures. For a substance in solution, the standard state refers to 1 molar concentration. And if we are talking about a solution here, so the substance should be in standard state when it is having 1 molar of concentration. Okay, so we define the standard state of a substance thermochemically. Okay, so let's move to the next topic, that is heat or enthalpy of reaction. So what is enthalpy of a reaction? It is the amount of heat absorbed or evolved at constant pressure when the quantities of substance indicated by thermochemical equation have completely reacted. It is denoted by delta H subscript R. So the enthalpy of a reaction, if a reaction is happening, so the enthalpy of that reaction is the amount of heat that is absorbed or evolved at a constant pressure by that reaction when the quantities of the substance indicated by thermochemical equation have completely reacted. When the reaction have completely when the reaction is completed, then the amount of heat absorbed or evolved at constant pressure is the enthalpy of that reaction. Okay, it is denoted by delta H R subscript. So R is for reaction. For example, here a combustion reaction for the methane is given, and methane with reacting with 2 molecules of oxygen is giving us CO2 and 2 molecules of water. And the del HR, that is enthalpy for the combustion reaction of methane, is minus 890.3 kilojoule. Okay, so delta H naught R is sum of enthalpies of products minus sum of enthalpies of reactants. That is, del H naught R will be equal to sum of enthalpy of products minus summation of enthalpy of reactants. We can write it in the symbol form like this. Okay. So, what is standard enthalpy? So, it refers to the standard enthalpy of formation when reaction is carried out at a standard conditions, like 1 atmosphere pressure and at 298 Kelvin. And it is denoted by delta RH naught. You can see the difference here, enthalpy of a reaction and standard enthalpy of formation. Okay, so if the enthalpy of products will be equal to enthalpy of reactants, then the change in enthalpy is 0 because both the enthalpies are equal, so no change will happen. Okay, second condition is that if enthalpy of products is greater than enthalpy of reactants, so if we see through this equation, so del H will become positive and the reaction is said to be endothermic. Okay, and for the H of products is less than H of reactants, del H will become negative and the reaction is said to be exothermic. So these are the conditions we have to keep in our mind while calculating the enthalpy of any reaction. Okay, so factors influencing enthalpy of reaction. So various factors that affects the enthalpy of reaction are physical state of reactants and products. So what is the physical state of our reactant or products, whether they are in gaseous form, whether they are in uh, solid form, it will affect. Like we calculate the enthalpy of vaporization, we calculate the enthalpy of fusion. So they are for different states change for matter. So enthalpy will also change for different state or physical state of reactants and products. Second, allotropic forms of elements involved. So allotropic formed is a different structural modifications of same element in same physical state. Okay, so if this is happening, this also affect the enthalpy of that reaction. Third is chemical composition state of reactants and products. So chemical composition state of a reactant or a product will also affect the enthalpy of the reaction. Like if our compound or if our molecule is the isomer of some other, so they both have the different amount of enthalpy. Okay, and what type of bond will be present, hydrogen bond, covalent bond, ionic bond, this will also affect the enthalpy of reaction. So chemical composition state will also affect the enthalpy of the reaction. Fourth is amount of reactant. So how much reactants we have, this also affect the enthalpy of reaction, and the temperature on which the reaction is going on, and the reaction conditions, like whether the reaction is happening in the presence of some catalyst or not, whether it is heating or not. These all are the factors which will affect the enthalpy of a reaction. So types of standard enthalpy of reaction. So let's see different types of standard enthalpy of reactions. First is standard enthalpy of formation, denoted by delta H naught of F, and it is the standard enthalpy change for the formation of 1 mole of a compound from its elements in their most stable state of aggregation. For example, there is a carbon which is in graphite form, allotrope form, plus 2 molecules of H2 will give you methane. The delta H naught F, that is standard enthalpy of formation for this reaction, is minus 74.8 kilojoule per mole. Okay, so enthalpy of a formation of an element at standard state by convention is taken as 0. For example, enthalpy of formation of magnesium, aluminium, sodium, hydrogen, oxygen, etc. is taken as 0. So this is a point to remember, that enthalpy of formation of an element at standard state by convention is taken as 0. And the standard enthalpy of the chemical reaction is given by the standard enthalpy of chemical reaction is equals to standard enthalpy of formation of product minus standard enthalpy of formation of reactants. Okay, so this is the equation, and here we can see that del F H naught P equals to standard enthalpy of formation for products, and del F H naught R equals to standard enthalpy of formation of reactants. Second enthalpy is standard enthalpy of combustion, that is delta H naught C. So it is the standard enthalpy change per mole of a substance when it undergoes complete combustion. Okay, so as the name is combustion, standard enthalpy of combustion. So in the combustion reactions, we use the standard enthalpy of combustion. So it is the standard enthalpy change per mole of a substance when it undergoes complete combustion. So the per mole of substance is undergoing a complete combustion, then we use the standard enthalpy of combustion. For example, again the combustion reaction for the methane giving CO2 and 2 molecules of H2. So the combustion standard enthalpy of combustion is minus 192 kilocalorie per mole. So del H combustion, that is standard enthalpy of combustion, is always negative, but for certain reactions it is positive. For example, this two reactions is given, N2 plus oxygen will give you 2 molecules of nitric oxide. Here, their combustion enthalpy of combustion will be positive, and F2 plus half of O2 will give you OF2. Their enthalpy of combustion will also be positive. Just to represent that this is the enthalpy of combustion. Wait a minute. Okay. So for both of these reactions, the delta H combustion enthalpy of combustion will be negative. So some of the reactions, for the certain reactions, it will be positive. Otherwise, it will be always negative. Okay. So third will be enthalpy of neutralization, represented by del H naught N. So it is the amount of heat liberated when 1 gram equivalent of an acid is completely neutralized by 1 gram equivalent of a base. So when the neutralization happens and the 1 gram equivalent of acid completely neutralizes 1 gram equivalent of base, then we use the enthalpy of neutralization. Del Hn is constant for strong acid and strong bases. That is, del Hn will be minus 13.7 kilocalorie per mole or minus 57.27 kilojoule per mole. So this is constant. Either you are using a strong acid or a strong base in a neutralization reaction, their enthalpy of neutralization will be constant, that is this. In kilocalorie, minus 13.7. In kilojoule, we have minus 57.27. So we have given this equation that HCl reacting with NaOH. So strong acid, strong base, neutralization reaction is happening, forming a NaCl compound and H2O, and the delta Hn, that is enthalpy of neutralization, will be minus 57.27 kilojoule per mole. For a weak acid against a strong base or a weak base, the numeral value of del Hn is always less than 13.7 kilocalorie. Okay, so if we are taking a weak acid against a strong base, the del Hn is always less than 13.7 kilocalorie. Due to the fact that here the heat is used up in the ionization of weak acid or weak base. Okay, that's why the enthalpy of neutralization will be less than 13.7 kilocalorie, which is a constant enthalpy of neutralization for a strong acid and strong base reaction. The absolute value of heat of neutralization of HF molecule is more than 57.3 kilojoule. This is due to very high heat of hydration of fluoride ion. So there is a note here, thing to notice, that when the absolute value of heat of neutralization of HF acid is more than 57.3 kilojoule. This is due to very high heat of hydration of fluoride ion, and this is the reason that why the heat of neutralization will be more than 57.3 kilojoule. This is the point to remember. Fourth enthalpy is standard enthalpy of atomization, represented by delta H naught A. It is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. So when 1 mole of bond will break completely to obtain the atoms in the gas phase, the enthalpy of atomization will be used. In case of diatomic molecules like X2, the enthalpy of atomization, bond dissociation enthalpy, and bond enthalpy are same thing. Okay, so when we are talking about a diatomic molecule, the bond dissociation enthalpy, bond enthalpy, or enthalpy of atomization are same thing. Fifth, lattice enthalpy, delta H lattice. It is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in gaseous state. Okay, so when the 1 mole of ionic compound dissociate into the gaseous state ions is happening when the lattice enthalpy will be used. So here NaCl compound is dissociating into Na positive, sodium positive, and chloride ion. So the delta H naught lattice for this reaction is minus 787 kilojoule per mole. Next, sixth, enthalpy of hydration, delta H hydration. So it is the enthalpy change when 1 mole of anhydrous or partially hydrated salt combines with required number of moles of water to form the specific hydrate. So when a anhydrous or a partially hydrated salt combine with the water molecule or a given number of water molecule to form the hydrate, the enthalpy of hydration will be used. So in this reaction, you can see copper sulfate reacting with the 5 molecules of water, giving this complex CuSO4.5H2, right? And here the del H hydration is minus 78.21 kilojoule per mole. During dissolution, physical state of the compound changes. So when we are dissolving the compound or a molecule in the water, the physical state of a compound change. While during hydration, if we are doing a hydration of a molecule, there is no change in the physical state of the compound. Okay, so you can see in this reaction also that we are doing the hydration of CuSO4. So CuSO4 initially is in solid state and the final product will also be in solid state. So no change in the physical state of the compound happened. Okay, seventh enthalpy is standard enthalpy of solution, that is del H naught of solution. So it is the standard enthalpy change when 1 mole of a substance dissolve in a specified amount of solvent. So del H naught solution is given by del H of lattice minus del H of hydration. Okay, this is important. Integral heat of solution is enthalpy change when 1 mole of solute dissolved in a pure solvent to form a solution of desired concentration. Differential heat of solution is the enthalpy change when 1 mole of solute is dissolved in such a large volume of solution so that no enthalpy change occurs on further dilution. That will be differential heat of solution. Okay. So if the solubility of a substance is known at two different temperatures, okay, the mean molar enthalpy of solution over this temperature range can be calculated by applying an equation similar to Van 't Hoff equation. And this is the equation that log S1 divided by log S2 equals to del H upon 2.303 R multiplied by the difference of fraction of T1 and T2. Okay, and here S1 and S2 are solubilities and T1 and T2 are temperatures respectively. So we can use this equation if we know the solubility of a substance at two different temperatures T1 and T2. So the mean molar enthalpy of solution we can calculate, that is delta H over the range of the given temperature using this equation. Eighth is standard enthalpy of hydrogenation. Okay, so it is the amount of enthalpy change that takes place when 1 mole of unsaturated organic compound is completely hydrogenated. So when an unsaturated organic compound, which is 1 mole, gets completely hydrogenated, the standard enthalpy of hydration gets in image. Okay. Ninth is standard enthalpy of dilution. So the standard enthalpy of change when 1 mole of a substance is diluted to such an extent that on further dilution no heat is evolved or absorbed is termed as standard enthalpy of dilution. Okay, so in the dilution standard enthalpy of dilution case, when 1 mole of substance is diluted, that on further dilution no heat is evolved or absorbed, this is termed as standard enthalpy of dilution. 10th is standard enthalpy of transition. So it is the enthalpy change when 1 mole of the substance undergo transition from one allotropic form to the another. So here the allotropic forms will play a role, that when one allotropic form of a atom or a element converts or convert from one allotropic form to the another, a substance undergo transition from one of its allotropic form to the another form, then the standard enthalpy of transition is used. So you can see here that sulfur in the rhombic state going to the sulfur in the monoclinic state, the standard enthalpy of transition for this process is minus 13.14 kilojoule. 11th is standard enthalpy of fusion. So del H naught of fusion, it is the enthalpy change that accompanies melting of 1 mole of a solid substance. So when 1 mole of a solid substance get melt, the standard enthalpy of fusion is used. So we can say that the standard enthalpy of fusion is equals to standard enthalpy of freezing in negative sign. Okay, because it is the opposite process. 12th is standard enthalpy of vaporization. So it is the amount of heat required to convert 1 mole of liquid into its vapor state. So when liquid of 1 mole convert to the vapor state, then this enthalpy will be used. So del H naught of vapor, that is standard enthalpy of vaporization, is equal to negative of del H naught standard enthalpy naught enthalpy of condensation, because they are the opposite processes. Okay, so 13, and it is standard enthalpy of sublimation. So at standard conditions, change in enthalpy when 1 mole of a solid substance sublimes is called standard enthalpy of sublimation. So when the sublimation happened, we use the standard enthalpy of sublimation, and we can write that the standard enthalpy of sublimation equals to standard enthalpy of fusion plus standard enthalpy of vaporization. Okay, because on combining these two processes, the sublimation happens in a single process, in a single step. 14th and last enthalpy is enthalpy of ionizations. It is the amount of enthalpy change that takes place when 1 mole of a covalent compound on dissociation in water splits to produce ions in the solution. So when we dissociate a compound, 1 mole of covalent compound, to produce the ions in the solution, the enthalpy of ionization used, you can see here the ethanoic acid going and dissociating into the two ions, that is CH3CO minus and H plus. And the enthalpy of ionization for this reaction is minus 55.43 kilojoule per mole. Okay, now let's study about the Hess law of constant heat summation. The enthalpy change in a particular reaction is always constant and is independent of the path by which the reaction takes place. So whether a reaction is taking place in 2 steps, 3 steps, 1 step, the enthalpy change of that particular reaction is always constant, remains constant. Okay, like you can say here, A is going to B, or either A is going to C, then going to D, then D is going to B. Okay, and these are the various enthalpies for every process. A to B del H, A to C del H1, C to D del H2, and D to B del H3. So in other words, we can say the total heat change del H accompanying a chemical reaction, that is a total heat change for a chemical reaction, is same whether the reaction takes place in 1 step or in more steps, as I said. According to Hess law, heat of summation is given as del H equals to del H1 plus del H2 plus del H3. Okay, you can relate by this form, this diagram. So del H1 equals to del H1, del H equals to del H1 plus del H2 plus del H3, right? Because A to B is a single step of having, enthalpy del H, but A to B can happen in different steps like A to C, C to D, D to B. So the enthalpy will be the sum of, the single step enthalpy. And some applications of Hess laws are, so it is used in determination of heat of formation, and the determination of heat of transition, used in determination of bond enthalpy of a bond or a molecule, and in determination of resonance energy of any molecule. So here it is a new term, resonance energy. So what is resonance energy? It is experimental heat of formation minus calculated heat of formation. So whatever the heat of formation is taking place or is used, the experimental one minus calculated one will be the resonance energy. Okay, so the bond energy or enthalpy. So when a bond is formed between two atoms in gaseous state to form a molecule, some heat is always evolved, which is called bond energy or bond formation energy. Okay, bond formation energy or bond energy is the heat evolved when in a molecule a bond is formed. So bond dissociation energy is the amount of energy required to break that bond which just formed. Okay, so bond dissociation is the bond dissociation energy is amount of energy required to break or dissociate the bond of a particular type present in one molecule of the compound. Bond energy is taken as average value of dissociation energies of same type of bonds present in various molecules. This is a point to remember. Since a chemical reaction involves breaking of old bonds in reactants and formation of new bonds and products, the enthalpy change of a reaction is given by del HR, that is enthalpy change of a reaction, equals to sum of bond energy of products minus sum of bond energy of reactants. In a polyatomic molecule containing two or more covalent bonds between same atoms, for example in CH4, the term average bond energy is preferred in place of bond dissociation energy. So any molecule which is polyatomic and having two or more covalent bonds between the same atoms, we can use the term average bond energy in the place of bond dissociation energy. So for CH4, average bond energy of CH bond will be bond dissociation energy of CH4 molecule divided by 4, as 4 bonds are present. Okay. Bond dissociation enthalpy values are negative if bond formation occurs, whereas bond energy values are positive if bond dissociation occurs. So there's two cases. If the bond formation is happening, then the enthalpy or bond dissociation enthalpy will be negative. If the dissociation or bond dissociation happening, then the bond energy value will be positive. Okay. So the factors affecting bond enthalpy. Various factors affecting bond enthalpy, like size of atoms. Smaller the size of atom, more closer the atoms to each other during bonding. Hence, larger is the bond enthalpy. For example, order of bond enthalpy of halogens is given here. So it is smallest in fluorine molecule and highest in chlorine molecule, then in the bromine molecule, and then in the iodine molecule. As we said that smaller the size, more will be the bond enthalpy. This is the order in the halogens for the bond enthalpy. Bond enthalpy of fluorine. You can see here that chlorine molecule has the highest or largest bond enthalpy, but fluorine is smaller than chlorine. Still, the bond enthalpy of fluorine is less than chlorine. Why? So bond enthalpy of fluorine is smaller than chlorine because of high degree of lone pair repulsion in F2 due to its smaller size. So its size is so small that the lone pairs of F2 molecule will have a lot of repulsion. That's why they don't need that much bond enthalpy to break their bond. Okay, that's why the chlorine bond enthalpy is larger than the fluorine molecule. So second factor is electronegativity. So larger the electronegativity difference between two atoms which is bonded, more is the polarity in bond, and thus more is the bond strength as well as bond enthalpy. So electronegativity will also affect the bond enthalpy. If the bond is more polar, that means electronegativity difference between the two bonded atoms is more, then the bond enthalpy needed will be large. Okay. So for example, in HF it is the highest, and then in OH bond, and then in NH bond. Okay, so this is the decreasing order of the bond enthalpy. Third factor which affect the bond enthalpy is bond length. So shorter the bond length, more is the bond dissociation enthalpy. And fourth one is number of bonding electrons. So as the number of electrons involved in the bonding increases, strength of the bond increases, and this increase the bond enthalpy, right? So here you can see C triple bond C having 3 pair of electrons, right, which is involved in the bonding. C double bond C having 2 pair, and C triple single bond C is having 1 pair. So more the number of electrons involved in the bond, more will be the bond enthalpy. Hence, this is the correct order or decreasing order of bond enthalpy for carbon, double, triple, and single bonds molecule, right? So next major topic which we're going to study is calorimetry. The experimental measurement of the heat change of a reaction or enthalpy change is known as calorimetry. And in the laboratory, heat changes in physical and chemical processes are measured with the calorimeter, which is an insulated container designed to minimize heat exchange with the environment. So calorimeter is a instrument by which we can measure the heat changes during any physical or chemical process. And calorimetry is the experimental measurement of that heat change of a reaction or enthalpy, right? So calorimetry is a phenomenon, calorimeter is an instrument. So Q is equals to mc del T, which can be written as capital C del T, and heat capacity, that is capital C, equals to mc. Okay, so del T can be written as T final minus T initial, where small m is the mass of the substance in grams or kg, small c is the specific heat capacity, and capital C is the heat capacity. So for the endothermic change, if a reaction is going endothermic, so Q is positive, we know that. And for exothermic change, Q is negative. So heat will be positive for endothermic change and heat will be negative for exothermic change. You remember what is endothermic and exothermic, right? Exothermic means transfer of heat to the surroundings and endothermic means transfer of heat from the surroundings. Okay. Constant volume calorimetry or BombCalorimeter. So heat of combustion is measured by placing a known mass of a compound in a constant volume BombCalorimeter, which is filled with oxygen at about 30 atmosphere pressure. On ignition of sample electrically, there is evolution of heat, which can be calculated by recording the rise in the temperature of the water. So we are just describing the structure of BombCalorimeter or the how the BombCalorimeter works. Heat lost by the sample will be heat gained by the water will be equal to, and they both will be equal. So Q of combustion, that is heat lost by the sample or during the combustion the heat evolved, will be equal to minus of sum of Q of water plus Q of bomb. So heat of bomb and heat of water will be added, and it will be equal to, in the M or C terms, M of water into C of water plus M of bomb into C of bomb multiplied by del T. Okay, so Q of combustion will be equal to del E of combustion, that is combustion in BombCalorimeter at constant volume. Therefore, del H of combustion will be equal to del E plus del NGRT. Okay, so these are some experimental derivations we used in the BombCalorimeter phenomena. The calorific value of a fuel or a food is the amount of heat in calories or joules produced from the complete combustion of 1 gram of fuel or the food. So calorific value we can find out by this formula. So del H of combustion divided by molecular mass of that particular fuel or food for which we are finding the calorific value. So we have studied the BombCalorimeter here. Okay, so we are at our summary slide. So these are some major things which we have covered. The standard state of a substance is its most stable form at 1 bar pressure and specified temperature, typically 25 degrees Celsius or 298 Kelvin. Okay. Heat of reaction or enthalpy change, del H, quantifies the energy change during a chemical reaction at constant pressure. Energy change when 1 mole of a compound forms from its elements in their standard state is called standard enthalpy of formation. Hess law of constant heat summation states that the total enthalpy change for a reaction is the sum of enthalpy changes for individual steps regardless of the pathway taken. So we add all the enthalpy changes which happened at every individual steps, and we have which will be equal to the total enthalpy change during that reaction. And calorimetry is the measurement of heat changes in physical and chemical processes using a calorimeter. Calorimeter is a device. Okay. Thank you.